moving on to the agenda. So today I wanted to first start with something with very basics because we have around 1 hour, 1 hour, 15 minutes. I thought it's important that we start with the basics and then kind of motivate why do we need distributed training and three of the important strategies that are currently used, like DDP, pipeline parallelism, and FSDP techniques. And I'll conclude it with some general remarks and then some time for questions. So at any point, if you have any questions, you can just raise your hand or just interrupt me. That's also okay. But let's try to make it more interactive because it's an online session. So always feel free to ask questions whenever you feel like something is missing or if something is unclear. To start with the basics. So here I wanted to start with some very basic slides because understanding how a neural network training works is important before we dive into the explanation of how distributed training works. So here I wanted to start with a simple example called MNIST. MNIST is basically a simple task of recognizing handwritten digits. So it's just one handwritten digits like 0 to 9 written in different ways. And then the goal is to recognize whether a number between 0 and 9. Sorry, I clicked the wrong icon all the time. And then, so the data set looks like this. So in these blue boxes, you can see the handwritten digits, and on the next to it, what is the expected output. So a handwritten 0 should be recognized as 0, and so on. So this is how the data set looks like. As you can see, some digits are very difficult to read. Some are very easy to read. Sometimes 7 looks like 1. Sometimes 1 looks like 7. So this is just to give you an example of how what the task is. Maybe most of you are familiar already with the task. Just wanted to show. So here I wanted to explain a simple neural network training setup. So for the handwritten digit recognition, let's train a neural network with 3 hidden layers. Then each hidden layer has 16 neurons or activations. And then at the output, you have 10 classes, which belong to one of the digits between 0 and 9. So let's use this as an example. So how it works in practice is you have a handwritten digits, and then you reshape this 28 by 28 dimensional image into one vector containing 784 points. And then you send it to 2 hidden layers. And then at the output, you get the predicted results. So basically, first we transform this 28 by 28 dimensional image into a long vector. And then at the output, you want to see a 9 as the predicted number because that's it looks like a 9. So how this prediction happens is through hidden layers, and these hidden layers, what defines these hidden layers is the weights and biases. I assume most of you know it, but just again, starting from the basics. So a neural network consists of several hidden layers that capture different patterns in the input data typically. And then these hidden layers are trained or learned during the neural network training phase. So when you're training a neural network, it means that we want to learn what is the best set of weights in the hidden layers that will give me the right answer at the output. And these weights need to be learned. And in this example, we have around 13,000 weights to learn. So at the input, we have 784 dimensional input, which is the reshaped image. And then we have 16 hidden states, and then 16 biases for it. And then the hidden state outputs are connected to another hidden layer containing another 16 hidden states, then 16 biases, and the final layer we have 10 outputs. and then 10 biases associated with it. So in total, we have around 13,000 weights to learn for this example. So how do we learn these hidden layers? So everybody probably knows about backpropagation. So backpropagation is the underlying algorithm that is used to learn these weights, or in short, like used to train these neural networks, because training means learning these weights, basically. So when you're starting, you initialize your network with random weights. You don't know what is a good set of parameters to initialize, right? So we just initialize all of the connections with random weights, and then we pass an input to it, say 3 here, but at the output, it will just generate trash because nothing is learned yet. It's just random initialization. But then from this point, what we do is, so this is the expected output. So the input is 3, so at the output we expect 3 at the output. But and then we compare the predicted output with the expected output, and then we compute some cost out of this. And this in this example, the loss is mean square error. So basically, we compute the difference between the predicted value and the expected value, take the square of it, sum all of them together, and that's the cost of 3, predicting 3, using the current set of weights. And then in backpropagation, a well-known approach is to do compute the gradients and then update the weights using the gradients. So that's how backpropagation works. Again, I don't want to go into why backpropagation works or how gradients work, because I assume most of you know about what gradients are and what backpropagation is. So the goal is to learn all the 13,000 weights using several training examples, not just with one example, but instead we look at lots of training data. And then we pass at a time a batch of data to the model. So instead of passing one sample, we pass, like in this case, we pass around 20 samples, right? Yeah, 20 digits to this model. And then we compute the cost for every sample, and then we sum them to one number, and this is called the loss function, or C of W. And then during backpropagation, the goal is to minimize the cost, because the cost kind of quantifies how good the hidden layers are in predicting the right digits. If the cost is too high, it means that the neural network is doing a bad job in predicting the digits. So the goal is to reduce the cost, then so that the loss goes down, and the weights also get updated so that the loss gets down. And over time, during the training process, we update the weights of the neural network so that we minimize the costs. And this is where we use gradient descent, and then backpropagation, as we use chain rule to powers over the neural network. So we start at the output layer, then we compute the derivative with respect to the output weight, and then we apply chain rule to compute the gradients with respect to the weights. And then these weights are updated using a small multiple of the derivative. So we have one loss function, and then this is the derivative with respect to some weight. And then we update the weights with a small multiple. So this is basically what backpropagation does. A neural network training involves, first you have to define a loss function. In this example, it's a mean square error, but depending on the use case, it can be, for example, LLMs are trained for minimizing the next token prediction loss. The nutshell is, we have some predicted output and the expected output. We compute some loss between the two. Then we compute the gradients with respect to weights, update the weights with a small weighted version of the gradient, and then you update the weights. And in that process, your cost will go down. And that's what backpropagation does. So to summarize, neural networks contain weights and biases that must be learned. So initially we start with random initialization, and during the training process, we use backpropagation. And then, yeah, of course, we need a cost function to compute the gradients. And then we use backpropagation over several training batches and also over several training epochs to keep on updating the weights and biases to arrive at a generalizable weight, because we don't want to optimize the prediction performance on a single digit, but rather the neural network should be able to predict all the digits between 0 and 9. So this is why we train it over multiple batches and epochs. And it uses a chain rule to compute gradients. So this is the summary of the first section. It's the very basics. I know most of you are already aware of it. It could be boring for some of you, but just wanted to cover this because these terms will appear in the next slides. So this concludes my first section of the talk. So if you have any questions here, feel free to ask. Okay, so I will move on to why the next section on to motivate why do we need distributed training. So what consumes memory when training a neural network? And yeah, now that we have established the terms like what backpropagation means, what gradients mean, what weights and biases mean, let's go to a bigger model. Let's take a 7 billion parameter model, which is still like a small model in today's standards. But let's look at a 7 billion model and how much memory it would take to train such a model on a GPU. So in the bottom section, you can see I'm considering the latest GPU from NVIDIA, which is AH100. It has 80 gigabytes of RAM. So it's one GPU machine. And then if I want to train a 7 billion parameter model, then I have 80 gigabytes of memory, right? Is it enough? Let's take a look at what consumes, what are the memory requirements for training a 7 billion model. So the first component is the model weights and biases itself. So the 7 billion parameter model means it contains in total of 7 billion weights and biases. And if we use float 16 precision for each weight, then that itself will take 14 gigabytes of memory, just loading the weights, the parameters of the model. And the second component during training is gradients, because for backpropagation, we need gradients. So typically it's the same size as the model parameters. So for 14 gigabytes of weights, then you need the same size of gradients. So it consumes another 14 gigabytes. Now we are at 28. And next one is optimizer states. So for backpropagation, we compute only we update the weights by only a fraction of the gradient. So we scale the gradients with some small number. And how is the small number calculated? That's where the optimizer comes into place. For example, Adam is a well-known optimizer. And Adam stores momentum and variance parameters. So basically, 2 times the number of parameters. So the weights and biases took 14, the gradients took 14, and now the optimizer states will take 28. So now in total, out of 80, he consumed 56 gigabytes. Is that everything? Weights, gradients, optimizer. Now you think that, yeah, I have still 24 gigabytes left in my memory. So that's enough to load my training data and then run forward pass and backward pass through the model. But that's not everything. That's the hidden thing. So the biggest memory eating component is none of these three. It's actually the activations. So to compute the gradients, we need to keep in memory the output of every activations, every hidden layer activation. We have to keep them in memory. So as we in a transformer layer, you have within each transformer block, you have a self-attention block which contains three matrices, query, key, and value matrices. It also has two feed-forward neural networks. So within one transformer block itself, you have like 7 or 8 uh, activations happening, and you have to and with such 7 billion parameter model, you have several transformer blocks, and you have to store each activation in memory. And this takes the most memory when we are training the model. For example, in this case, if you use a batch size of 8 and 2048 long sequence and 32 hidden layers, it consumes around 200 gigabytes of memory. So for a 7 billion parameter model to store all the intermediate activations, that's how much it would take. So now suddenly, all on a sudden, it takes 256 gigabytes, but our GPU can only fit 80 gigabytes, and suddenly we run out of memory. So this is why even to train a 7 billion parameter model, 80 gigabytes of GPU is not enough. And that's why we need distributed training, or to distribute our training across multiple GPUs. And this is also how these large LLMs are trained. So as you saw, a single GPU with 80 GB memory is not enough to train a 7 billion parameter model. Total memory required is around 256, way more than what we expect with float 16 precision, which is these days float 16 or B float 16 is this industry standard in training LLMs. So it's a reasonable number. So we need to distribute memory across multiple GPUs to train GPUs. And the other motivation is for distributed training is, even if we have a huge GPU that can fit, 256 gigabytes in one GPU, we are training also on massive amount of training data. So for example, to give you a number, if you can fit the GPT-3 model in one big GPU, assume you have like one big GPU of, I don't know, 1,000 gigabyte memory or 2,000 gigabyte memory. Then to train GPT-3 in that single GPU will take 350 years, because that's the amount of training data it has to process. So training on any question or okay. Um, so we need distributed training for two reasons. One is to fit to train large models, and also the second reasoning is to speed up um, training. Because we all these LLMs are trained on massive amounts of training data. So even if for the model to see all the training data, yeah, I think I hear some. Yeah, okay, it's muted. Yeah, to be able to hear all these, sorry, here, just for this, see all this training data at least once. Yeah, we need a lot of time. It takes a lot of time, and then if we can parallelize it over multiple GPUs, then it can really speed up. So these are the two motivations. Any questions now? Because now I will explain three of the different techniques that we use for distributed training. All right, so let's move on to the first technique I wanted to discuss today. It's called distributed data parallelism. So that's the first popular technique. But in this case, we assume that the model can fit in a single GPU. And then we only want speeding up our training. So suppose you have a model, maybe 1 billion parameter model, and then you have so much training data. then you can do the training on a single GPU, but it takes 2 weeks to finish training. But then you can instead use 4 GPUs, parallelize it, and then you can do the same in like 5 days. Oh, sorry, it's 4 times faster. So something that takes 12 days can be done in 3 days basically if you parallelize your training across 4 GPUs. And this is important for fast experiment iterations. Suppose you want to prototype different models, small data sets, and then if you want to run multiple experiments with it, then DDP is a good approach. Like you can parallelize it across multiple GPUs, so that one experiment doesn't take 2 weeks. Every experiment it takes only 2 or 3 days, and then you can try the next experiment. So, sorry. Um, So as I said, the underlying assumption here is not huge models, but you assume that the model can fit on a single GPU. And so it's typically like 1 billion parameter or 2 billion parameter model, but the goal is to only speed up your training. So I will explain it in a schema, like in a picture next in the next slide. But on a high level, what it does is creates a copy of the same model in multiple GPUs, and then every GPU gets a different training data, and then it will train the model, but with different data. But so it will train the model in parallel. So here the data is parallelized. The model is not distributed across. It's the same model being copied over to the different GPUs. So that's why it's called distributed data parallelism. So every GPU gets a different batch, basically, and processes it. But it will be clear in the next slide. So to explain it visually, suppose we have 3 GPUs, and then we have our training data uh, organized into batches. And then we have our initial model. And then when the training starts, what it does is every GPU gets a copy of the DNN model. So again, as I said, here the assumption is the model can fit in a single GPU. And then now we have 3 copies of the same model. Then you see each GPU get a different batch. GPU 0 gets first batch, GPU 1 gets the second batch, GPU 2 gets the third batch. And then each GPU will do the forward pass, and also it will compute the backward pass separately. But and now you get 3 separate gradients. So this gradient belongs to the batch 0, this gradient belongs to batch 1, and this gradient belongs to batch 2. But if we individually update these models, then the problem is the models will get out of sync, because the weights will be updated differently between different GPUs. This is definitely something we want to avoid, because the model should learn together. So we have to make sure that at any time, the model weights are the same in all GPUs. So what we do here is, now we have 3 gradients. We sent all of them to the primary GPU. So there is this additional communication between the GPU to sync the gradients. So all the GPU 1 and GPU 2 send their gradients back to GPU 0, and then GPU 0 will merge all the 3 gradients coming from all these GPUs, and then send it back. So it sends the merged gradients back to all GPUs. So now all GPUs get the exact copy of the gradients, and then each GPU will perform back propagation, meaning they update the weights. But now that all of them get the same gradients, the weight update will also be the same. So all GPUs will contain the exact model weights. So in the nutshell, what it does is it computes the gradient separately on each batch, and then they combine the gradients by communicating together, and then the merged gradients need to be sent back to each GPU. So this is the extra communication overhead needed. But we have now good inter-GPU communication protocols. So these inter-GPU communications go typically relatively fast. But this is also something that we do as a compromise, because now we can do forward and backward gradient computation in parallel. And then we have the extra overhead of syncing the gradients and also transmitting the merged gradients back. But then the weight updates happen with the same gradients. So at any time, all the GPUs will have the same model weights, but they always get different batches. So that's what DDP does. And to summarize some advantages and the limitations of DDP, the first advantage is it has a linear speed up, because the only overhead is communication of gradients between the GPUs. But as I said, these things can go fast. So most of the times you get like if you have three GPUs, you get 3 times speed up compared to training on a single GPU. If you have 12 GPUs, then something that takes 12 days can be done in 1 day, more or less. So that's the kind of speed up that you can get. It's this. Sorry, I moved too fast. I have to go back to the. Yeah. And it's relatively easy to implement it, because it doesn't involve complicated communication. It's only require communicating the gradients between the GPUs. But in the next techniques, you will see how complicated it can get in terms of how to sync different things. Um, and this other one is it's memory efficient. And the fourth one is because by memory efficient, what it means is most of the times the GPUs are computing something. The one GPU doesn't have to wait for another GPU for its computation. That's what it meant by memory efficiency. And it's typically good for large data sets, as I said, because it's useful only for small models, because your model needs to fit fully on a GPU. But when you have large data sets, then because you distribute the data across multiple GPUs, that's where you get most of the speed up here. To list some limitations, one is model size constraint. As I said, one constraint is the model has to fit on a single GPU. So you cannot go too big in terms of model size if you want to use TDP. There is a small communication overhead, because there is this gradient synchronization between the GPU, as I said, and not for very large models. And the bigger, one of the biggest, in my opinion, the limitations is the synchronization cost, because some GPUs can be fast with forward and backward pass, and some are sometimes slow. So to update the gradients, it has to wait for all the GPUs to finish one forward pass and backward pass. So suppose the first GPUs finish forward pass and backward pass, they already have their gradients, but they cannot update the weights, because they have to wait for the third GPU to finish computing the gradients, because they have to synchronize the gradients. So if there is a slow GPU, or if there is a training data sample that is corrupted, or it takes too long to compute the gradients, then during that time, the other GPUs has to wait without doing any computation. So it's a waste of compute if there is there are some slow GPUs in the mix. So that's everything I wanted to explain about DDP. And next, I'll move on to the next approach called pipeline parallelism. But before I move on, I wanted to pause here and, again, if you have any questions, you can ask. Yeah, I will count till tick, tick 1, tick, tick 2, tick, tick 3. No questions, and then let's move on to the next slide. Okay, the second approach is called pipeline parallelism. So after DDP, yeah, there was this limitation because there is always a model size constraint. You cannot train huge models with it. And in pipeline parallelism, what it does is it splits. Yeah, here we are looking at large models which cannot fit on a single GPU. So what it does is every neural network is comprised of different layers, right? Different hidden layers. So what it does is it splits the model into small segments, and then each segment is sent to each GPU. So suppose you have 32 layers or 60 hidden layers in your neural network. Then you split it into three, like the first 20 layers will go to GPU 1, middle 20 layers go to GPU 2, and the last 20 layers will go to GPU 3. So the model is also distributed across, model weights are also distributed across different GPUs. So that's how pipeline parallelism work. But then in pipeline parallelism, the data, the training batch flows through stages sequentially, because first it reaches GPU 1, uh, yeah, do the calculation with the segment 1, take the output of it, send the output to second GPU where segment 2 lives, then compute, run forward pass through segment 2, and so on. So this it requires passing the output of one segment to the as input to the next between GPUs. So as I said, we have to partition the big neural network into smaller segments so that each segment can fit in a single GPU. And there is a sequential flow, like the training data flows from one device to another, because each segment of the neural network is only available in certain GPUs. So to run forward pass, the data has to flow through each GPU. And I created a similar visual to explain it. So here again, we consider a scenario where we have three GPUs, and we have training data. In this case, we call it micro batches. That's why it's called MB0, MB1, MB2, and MB3. And in the bottom, let's take a neural network containing four layers, like three hidden weights, so that we can split each weight into each GPU for visual. But in reality, it's not each weight, but rather segments of the neural network. But here we simplify it for visualization purpose. So first, as I said, each GPU gets a segment of the model. So the first GPU gets the first weight, the second GPU get this middle portion, the third GPU gets the last layer. So so the model is distributed across different GPUs. And then in forward pass, yeah, the mini batch 0 is sent to GPU 0, runs the forward pass. Now it has the activations corresponding to the mini batch. I call it A0. And then in the next step, these activations from the output of the GPU 0 is sent to GPU 1. Then it will run forward pass, compute the activations here. But then at the same time, GPU 0 gets the next micro batch, because otherwise GPU 0 will stay idle the whole time. So we want to make the most out of it. We don't want GPUs to stay idle. So this is why immediately the activations are sent to the next GPU. The next mini batch will be pushed to GPU 0. The next step, the output of GPU 1 will be sent to GPU 2. The output of GPU 0 will be sent to GPU 1. And then GPU 0 will get the next mini batch. So like this. And then each will do its own forward pass. So now you can see in GPU 2, you have the output of mini batch 0. The forward pass for mini batch 0 is fully done. You can yeah, in GPU 3. And then for mini batch 1, it is at GPU 1. So it needs one more transfer to GPU 2 to get the final outputs. And mini batch 2 just started its journey. So it's starting at GPU 0. And here you can see a visual in the bottom, like device utilization timeline on GPU 1, GPU 0, and GPU 2, like which micro batches are um, sent in which GPU. So F0 is forward pass, F1 is forward pass for micro batch 1, and so on. And next, in the next step, it does two things. Because we already now have the output of mini batch 0 at GPU 2. Now we can start backward pass for micro batch 0 because its forward pass is finished now. So next step, it does two things. The first thing is, it first finished the forward pass. So that's, yeah, it first computes all the outputs. So now you can see the output of the mini batch 1 is now available in GPU 1. So the forward pass is now complete for mini batch 0 and mini batch 1. Mini batch 2 is at the second stage. Mini batch 3 just started its journey in GPU 0. And then, yeah, the GPU, the activations will get transferred to the next GPU in a sequence. So now the output for mini batch 2 is available at GPU 2, and then the intermediate output of mini batch 3 is available in middle layer. And then we also compute the output of mini batch 3. So now it only finished forward pass, no backward pass yet. It only finished forward pass, but we did it in a sequential way so that most of the times the GPUs are running something, doing some calculations. But now it's time to calculate the backward pass. So just like we did the forward pass, now we compute all the output for the four mini batches. Now we have to compute the backward pass. So first, it starts again at mini batch 0. It compute the gradient 0, and now the gradient 0 has to be sent to backwards to GPU 1, and then yeah, now grad 0 goes to GPU 1, and then the gradient of the mini batch 1 is computed in the last GPU. So now we are doing, just like we did forward pass in a sequence, we are doing the backward pass. So now we are slowly finishing up. Now we have the backward pass completed for mini batch 1, now mini batch 2, and now mini batch 3. So now it has completed one forward pass and one backward pass for 4 mini batches. And now it has 4 gradients. Now it has to sync the gradients for each weight and then update the weights. So that's the next step. And you can see here in the bottom picture, like device utilization timeline, not all GPUs are active because, for example, in this case, in the very last step, only the in backward pass, only the first GPU is doing some compute. The other two GPUs are just staying idle because there is no backpropagation or any computation happening there. So this is called the bubble problem. So it's the GPUs are active for a bubble of time, and then it has to wait for the forward pass and backward pass to finish before it can process the next. So every time this process repeats, the data flows through the model in sequence. Backward pass also has to happen in sequence. And then sometimes some GPUs are staying idle. You can see these empty spots in the device utilization timeline picture in the bottom. But this is for this reason, yeah, it's an efficient setup. It allows training large models, but there is some inefficiency because um, it has some CPU, sorry, GPU idle time. But we don't want our GPUs to stay idle during training because these big companies, they spend several millions of dollars in purchasing and maintaining these large compute clusters. So if you start a training, you have to better make full complete use of all the GPUs there. But one nice thing about pipeline parallelism is definitely that it can train large models. So it doesn't have any like model size constraints. It's just that it has this memory bubble problem that doesn't utilize GPU 100% of the time. So to summarize, so pipeline parallelism can handle large models because it really split the model across multiple GPUs. It's also called model sharding. And it's memory efficient because each GPU only stores certain segments assigned to it. So every GPU is responsible for a certain segment of the neural network. So per GPU, it doesn't require too much memory. And then it scales really. The model size, you can go, yeah, the model size can really go high, and then you can scale it up across several thousands of GPUs. You can split the model across several thousand GPUs. And then you can scale your model size. And this is also how, I mean, not exactly the pipeline parallelism, but this is one of the techniques that's used by these big LLMs, which contains several billions of parameters. Like GPT models are around 500 billion, sometimes even there is one model, I think, from DeepSeek, which is even 1 trillion parameters. So you really need to scale up, the compute. And this is also good for really deep or long networks because you can split the neural network in chunks or in segments, and then it can handle it. It scales up very well. The limitation is, as I said, there are these bubbles, meaning some GPUs will experience some idle time because it needs, the previous GPUs to finish the forward pass and backward pass to do its own calculation because it happens in a flow, sequential flow. And then there is also a lot of communication overheads because it has to pass not only the gradients. In DDP, the only thing that we had to communicate or synchronize was the gradients. But in this case, we have to synchronize the gradients and also the intermediate activations because the output of the activations has to be sent to as input to the next GPU. So there is this extra communication overhead. What I should have. Yeah, I'm sorry. I have to. Oh, yeah, okay. I'm back. And then, how do we schedule? So if we have to really orchestrate all this micro batching, like it has to follow this flow and when to start backward pass, when to pass one activation to the next. So there is a lot of complicated scheduling that needs to be implemented in terms of actually implementing it. Yeah, visually it looks nice, but to actually implement it in a flow and making sure that the communication between the GPUs are happening correctly and it actually operates in a meaningful flow that doesn't result in too much idle time. It requires some complicated implementation. So in that sense, it requires quite some complicated scheduling. Yeah, it also has to do some load balancing, meaning we are splitting the splitting the model into segments, and then we have to split it in a way that not just in the number of parameters, but also in terms of how much time it takes to compute each block. So we need to do this load balancing. Suppose I have a neural network. The first 30 layers are only, simple, fully connected layers, which are relatively fast to compute. And then the middle, I have all the transformer blocks requiring self-attention computation and everything. And in the end, I have again another set of fully connected layers. What happens is the middle GPU always has this huge compute requirement because the GPU 0 and GPU 1 contains only fully connected layers. The middle GPU has all the transformer layers. Then again, the other GPUs will have to wait for a long time because it has to wait for the previous GPU to finish its computation, right? So we have to carefully balance the compute load per GPU so that each GPU takes similar time to execute its forward pass and backward pass. This is another a problem when we deal with multi-GPU training. Like some GPU takes longer, some GPU compute faster, and then you have this waiting for the slow GPU problem. So we have to carefully so here, as I said, we are splitting the model ourselves. So we have to be careful the way we split the model so that we can balance the load in a meaningful way across different GPUs. So that ends the summary about pipeline parallelism. I hope you understood the gist of it. But again, if you have any questions, let me know. Okay. I will move on to the last and final technique I wanted to discuss today, which is called fully sharded data parallelism.
Divak,
Yeah,
there is a question in
yeah.
chat.
There is I cannot. Let me go back to the chat. Can I open the chat? Or can you read it for me? Yeah, okay, I can. I found it. I'm curious to know, is it possible to address this GPU idle time by shifting load to idle GPUs? Yeah, yeah, be of any help? Yeah. The first question is, idle time by shifting the load to idle GPUs. Yeah. So um, once you schedule a job, it's better. You cannot actually change, reshuffle the whole thing because the whole thing is scheduled. The way the data flows and the way forward pass and the activations are transferred across different GPUs. These things are already scheduled, and during runtime, I would say it's difficult to adjust it. But one thing you can always do is you can start your training, and then during training you can monitor each GPU and then see, okay, this GPU is taking too long. Maybe I will split that model segment into two and maybe add one more GPU to my training setup. So this way, it's more like ad hoc. You need to see uh, if there is a load balancing problem. So I think that answers your first question. And the second one is about can AI be of any help in some smart load distribution? Um, in general, no. I would say that's actually where humans are still useful. Yeah, AI can still it cannot really replace humans in every aspect. So this is it requires like quite some good engineering skills to be able to pull this off. And AI can still give you guidelines saying that, yeah, this segment has too many transform blocks, so it's better to split it into more GPUs. Yeah, it can give you these guidelines, but in the end, the scheduling itself, uh, to my knowledge, yeah, the way we do the load balancing and the way we do the scheduling, we don't use AI there. But It's also tricks of the trade, like knowing how to do it. It's basically engineering work, like how do we implement the whole thing. So AI can give you these insights, but I would say these are kind of known to engineers, so they will do these things. If Yeah, I hope I answered both of your questions, but if you have any follow-up questions, yeah, okay, thank you. And let me go back to my slide if there are no other questions. So FSTP. So the goal here with FSTP is, before with pipeline parallelism, I said that there is this bubble, like memory bubble problem, like some GPUs have to wait because the data is flowing sequentially through each GPU. And we want to reduce GPU idle time, basically, because the moment because training these large models are very, very expensive, and then we pay per uh, training time. So we pay per these cloud services, they charge you per hour. And if some GPUs are not used, then you are basically not making the most out of it. And this is where this fully sharded data parallelism technique come into picture. The goal here is to speed up training, make sure all GPUs are working all the time. So it's basically combining the best of DDP and pipeline parallelism. Let's keep it that way. So it's way faster also. I will explain how it works. So FSTP, it's an advanced training strategy. So here again, the model parameters are split across multiple GPUs, similar to pipeline parallelism. The model is split. But then it also takes principles of TDP, meaning each GPU gets a separate batch. It's not like in pipeline parallelism. One problem was the data always starts in GPU 0 and it is traveling through the entire GPUs. But that's also not efficient. And also it takes time because you can process like one batch at a time, right? And then in sequence. And FSTP combines the best of TDP, meaning every GPU still will get its own batch, and the model will still be sharded. So this is why it's called fully sharded. So the data is distributed across GPUs and also the models. So this is why it's called fully sharded data parallelism. So the model parameters are split across GPUs. So every GPU is owning a subset of the weights. And then the weights, yeah, I would skip this part. I will move on to the similar graphical visualization on how we can explain it. So again, let's take a case where we have 3 GPUs and we have a training data set which has three batches: batch 0, batch 1, and batch 2. I mean, we can have more batches, but let's take 3 batches in this case. And then we have a model which contains W1, W2, and W3. Like, let's, for simplicity, let's assume that these are like 3 different segments of a large model. W1 is one segment, W2 is another segment, W3 is another segment. So just like pipeline parallelism, each GPU gets a segment. So GPU 0 gets W1, GPU 1 gets W2, GPU 2 gets W3, the 3 segments. And then you say, okay, GPU 0 is the owner of segment 1 or weight 1. GPU 1 is the owner of W2, and GPU 2 is the owner of W3. So that's it owns it in a in a sense that I will explain it in the next step. So as I said, it also does DDP. So what I said is, what it does is every GPU gets its own batch. So GPU 0 gets batch 0, GPU 1 gets batch 1, GPU 2 gets batch 2. And then the first step is to compute the forward pass through W1, right? So batch 1 cannot start with W2. It always has to start at the input and then reach the output, right? So how do we compute the forward pass of batch 1 in GPU 1 and forward pass of batch 2 in GPU 2? So what it does is it broadcasts. So GPU 0 is the owner of this segment, right? So in the first step, it broadcasts these weights. So you can see the memory usage increases a little bit in these GPUs because it now extra has W1 and W2 copied from GPU 0. So GPU 0 will transmit W1 to GPU 1 and GPU 2. So there is a very small increase in memory usage because it's only in addition to its own model segment, it's additionally loading W1. Then it runs, and all the three GPUs run forward pass at the same time. So now we have the output after each activation for all GPUs, and immediately after the forward pass is done, it deletes the copy of the weights W1 and here and W1 here, so the memory usage is back to normal usage. So now at every GPU, the output of the first segment is finished, corresponding to each batch. Now it has to do forward pass through W2. We do the same. GP1 is the owner of W2, so it broadcasts the weights to other GPUs. So you can see in GPU1 there is a small increase in memory usage. In GPU1 GPU2 also has a small increase in memory usage. Then it does forward pass through the weight 2. Immediately after the forward pass is done, it's deleted. Now we have every GPU has activations of layer or segment 1 and output of layer 2 or segment 2 corresponding to each batch. You can here see that these are computed on separate batches, which also speeds up computation. And then the final step is to compute forward pass through W3. We do the same. GPU2 is the owner, so it transmits it W3 to all other GPUs. So GPU0 and GPU1 consume some extra memory because it now has to load W3. Then all GPUs at once compute the forward pass through W3, and immediately after the activations are computed, it discards the weights, and then it frees up the memory. So now it has all the activations corresponding to each batch. The next step, so the forward pass is done. So at any point, all GPUs are doing some calculation. No GPUs, so the GPUs are not waiting for any other GPU. All GPUs does the forward pass together through different segments of the layer. And now that it has all the activations, the forward pass is done. Now it has to do the backward pass. That's the same. It starts at the outputs. So to compute the gradient first, it has to go through W3. So W3 is broadcast. Then gradient is computed. Then W3 is immediately removed. Then W2 is broadcast. And then gradients are computed. And then W1 is transmitted, gradient is computed. Now it does forward pass and backward pass. Both are done. It has all the gradients. Now it does a synchronization between the gradients. So each GPU has full gradient for its own batch. Now it has to synchronize the gradients just like we do in DDP. We synchronize the gradients and update model weights. But the model weight update will only happen in the corresponding owners. So W1 updates will only happen in GPU 0. GPU 1 will not update W1 because it's not the owner of W1. So the W1 is always updated here. GPU 1 takes care of updating W2, and GPU 3 takes care of updating W3. So this is why I said each GPU is the owner of a segment. It takes care of transmitting the weights to other GPUs, and also takes care of updating the weights. And as you can see, at any point, all GPUs are doing some computation. So there are no GPU idle times in general, like one GPU waiting for another GPU to finish its computation. And also you can see that the training data forward pass is also happening in parallel, like, because it's not happening in a sequence. Rather, batch 0 and batch 1 and batch 2, these are computed in parallel. So this also speeds up. So it's basically, as I said, um, combining the best of both pipeline parallelism and data distributed parallelism. So this is kind of the state of the art in current neural network training, because it reduces GPU idle time. But then the overhead is at every computation, it has to sync the weights. So it has to move the weights between GPUs. And also it has to move the gradients. So it has to move the weights during forward pass and also during backward pass 2 times. And also it has to sync the gradients. So this is it requires some extra communication effort, because it increases the communication between GPUs. So this is what slows down the training a little bit. Whenever we have a communication between GPUs, that slows down. So we want to minimize it. But here we have modern technologies that really speeds up inter GPU communications, like fast interconnects and I forgot the name, NCCL library from CUDA, and it's NCCL or Nickel, as people call it. So these libraries will really speed up inter GPU communication. So to summarize the advantages, I think I already covered most of it, but the goal is the same as in pipeline parallelism. This is also memory efficient, because it splits the the model weights across multiple GPUs. And then it is also scalable, like pipeline parallel, because because the model is sharded. And then the memory management is dynamic, because the weights, only the required weights are synced across GPUs, only for computing a certain part. And then those weights are immediately removed from GPU memory to free up the GPU memory. And basically, as I said, it basically combines the best of data and model parallelism. The limitation is, as I said, there is quite some communication overhead, because there is frequent communication between GPUs in broadcasting the weights, and also broadcasting the gradients. And it's also the implementation is also a bit complex, but I would say it's simpler than pipeline parallelism. But then here, the crux is about the communication management, how the GPUs actually communicate between themselves. Okay, it's time for syncing weight 1 or syncing weight 2. So this communication management is one layer of complexity. And it doesn't make sense to do this for small models, because if your model fits on a single GPU, it's always better to go for DDP. Because as long as you can fit the entire model on a single GPU, you can avoid all the inter GPU communication. The only inter GPU communication needed during DDP is synchronization of gradients. And also it has a network dependency, meaning the GPU communication requires, it has to transfer data through the network cables connecting to GPUs, right? So that's, you need some fast network communication to run it at a reasonable speed. So that kind of concludes the three topics I wanted to discuss with you today. And I want to conclude, but before I wanted to conclude, I will quickly check the chat. I don't see any questions. And yeah, good question. Yeah, the sharding is applicable to optimize, like the optimizers as well. Yes, because these optimizer states, they also live in the corresponding GPUs. So because for every weight, there is a corresponding optimizer params like momentum and variance for Adam, and these are also sharded. So for segment one, GPU 0 is the owner, meaning it captures the weights. It also has the optimizer states corresponding to that particular weight, and it also takes care of the weight updates. So weight updates happens in one GPU that is responsible for a certain segment. Yes, the short answer is yes. The sharding is applicable to optimizer states. Yes. Um, all right. I lost my. Okay. To conclude, on a high level, how do you choose the right strategy? Right, there are all these different strategies. How do you choose which one to use when? So this is a simple, simplified flowchart on how deciding on the choice. So it's all depends on the model size. Does your model fit on a single GPU? If it's yes, then always go for DDP, because that's the fastest, it's the simplest, and also otherwise you run into all the inter-GPU communication overheads, which is not worth it. But if it doesn't fit on a single GPU, then you have two options, whether to go for pipeline parallelism or FSTP. So if you have really fast inter-GPU communications possible, then FSTP, because FSTP requires additional communication between GPUs in terms of really transferring data between transferring weights between the GPUs. So you need some fast interconnect between the GPUs. So if you have good infrastructure where you can easily communicate between two GPUs, then you can go for FSTP. But if your interconnections are slow, if this, synchronizing the weights between GPUs take too long, then we can go for pipeline parallelism, which still has some communication overhead, but it's not as high as FSTP. So this, and then in the ideal world, we always want to combine it with, if it's too large model, then we can always combine FSTP with pipeline parallelism, or you can also run multiple pipeline parallel models in parallel. So suppose you have 100 GPUs and one model shard happens across 25 GPUs. So you can have 4 such model training setup in parallel. Then you can do some parallelization there. So this is what we mean by combining it with TDP. But of course, it requires huge compute infrastructure, and that's what most of these big companies already have. They have access to thousands of GPUs, so they can easily scale up their training, and then they manage to train this multi-billion, like 500 billion or 600 billion parameter models in 1 or 2 months. It's simply because we have all these techniques in place, and because we have all this access to all these big compute clusters containing several thousands of GPUs. And just to summarize some key takeaways. So in this talk, we discussed three techniques. The first one is distributed data parallelism. So again, as a take-home message, this is the approach to use when you have small models. So it basically replicates the same model across GPUs. So there is no model sharding, or the model is not split. And then each GPU will get a different mini batch, and then it only has to synchronize the gradients. So the speed up is also typically linear. Um, the second approach is pipeline parallelism. So we can scale up the size of the model by splitting or sharding the model across multiple GPUs. There is a sequential data flow. The data flows through each GPU, and there is this GPU bubble problem because the data flows through each GPU. The one GPU has to wait for the output of the previous one. And the last one is FSTP, which is basically combining the best of pipeline parallelism and DDP. But it requires some extra communication overhead because it also has to synchronize the weights between, transfer the weights between GPUs. So you need some fast interconnects. And that's it. If you have any questions or discussion, yeah, I'm happy to do it with you. I hope you find it useful. I hope you learned something today. And yeah, it's time for questions if you have any. Thank you.
Deepak, I have a question. What about the support provided by frameworks like TensorFlow and PyTorch for distributed
Yeah.
data?
Good question. So most of these things, I mean, TensorFlow, I'm not sure because TensorFlow is deprecated, right? So TensorFlow, it's not actively maintained anymore. So for most of the companies, PyTorch is the current popular, and also the Hugging Face and Transformers library of Hugging Face. So one popular technique that we also make use of here is Hugging Face Transformers library. So they have a trainer class, trainer, yeah. And then it supports most of these things like FSTP or DDP. I never tried pipeline parallelism because it doesn't make sense, but I tried FSTP and DDP with Transformers package. So this work, I mean, the coding is not too much because most of the coding is there implemented for you. For example, and there is also this thing called PyTorch Lightning, which is also yeah, it's something similar to Transformers, but it has more advanced a distributed training strategy. There are more things like, there are other packages like Deep Speed from I think, yeah, it's from Microsoft, Deep Speed, and I think the other one is FSTP, which is basically from Meta, I think. So FSTP is present in Hacking Face Transformers, and also PyTorch Lightning is the other one. And then there are also these algorithms like Deep Speed and also something called Zero Optimizer, which also reduces memory footprints and GPU idle time and faster training. So there are most of these things are open source available. So once you have access to multi GPU environment, then setting up a multi GPU training is not super difficult because most of those are available in these open source models. Okay. Any other? I mean, yeah. Justin, I hope you answered your question, right? Or if you have any follow-up question. But to add, there are also other frameworks like JAX from Google, or because Google moved to JAX, from TensorFlow. So JAX also supports multi-GPU training. Then you have other like native NVIDIA setup called Nemo, RT, and all these packages also support multi-GPU training. Yeah. Yeah, but one thing is, if you want to discuss or if you have any questions, you can always reach out to me. I think I will share my email with Justin. And yeah, if you want to see the presentation, I can push it to my GitHub because it's not a PowerPoint. It's more like HTML. So I also published a blog post on this because I I have been working on this. So I thought, okay, I will write a blog post about it. So I will share the link to the. I haven't pushed the presentation to GitHub. So once I push it to GitHub, I can share the GitHub link with you, and I can share the link to my blog, and I can share my. Sorry, I can share my contact details. If you have any questions, you can always email me. Right. Yeah, hope you learned something today. And it was also fun preparing for this presentation. I also learned a lot in the process, and I also worked into these visualizations. It was very difficult to, I mean, I couldn't find any nice visualization on this, so I thought, okay, let's make one for the presentation. But in the process, I also learned a lot. So thank you for this opportunity, Justin, and keep doing this. I'm always happy to do this because it's also a good learning opportunity for me. And it's a bummer that, yeah, is this session fully online and there's no physical session for this? Yeah, it's a
Online
question
session,
to
sir.
Justin.
Online.
Sorry.
Fully
It's fully
online.
online. Okay. Okay. Thanks. So there is one next session, right? After this.
Yes.
Yeah. So if there are no other questions, I will share the resources with Justin, also my contact details, and then I think Justin can share it with the participants. And I don't know, there's an email list or what. But I
We have
will.
I'll share it there.
Okay, yeah. Give me some time. I need to push this to GitHub and stuff. So in the next couple of days, I will share these resources with you. Okay, so thanks a lot for attending and also for this opportunity. And yeah, it's been a while since I did the talk, so it was nice.
Thank you, Deepak, very much.
Thank you then. So I will drop the call because I have a meeting in like
Okay.
4 minutes. Yeah, so enjoy the rest of the session and thanks again.
Thank you.
Bye.
Dear participants, the next session at 7:40 p.m. We have a short break. Dear participants, welcome to session 2 of today's sessions. Today we have with us Mr. James Joy. James is a technology manager at Tata Elxsi Limited. He is a specialist in automotive embedded systems and a highly experienced AutoSAR architect, bringing over 2 decades of professional expertise in high-stakes domain of vehicle electronics. His rich background includes international consulting roles, having served as an AutoSAR specialist for Jaguar and Land Rover, and an external consultant for Hella in Germany, where he specialized in ECU software and bootloader technology. With a Master of Science in Software Systems and several key publications on secure automotive networking and AutoSAR migration frameworks, James Joy combines deep theoretical knowledge with extensive practical experience in crafting next generation of reliable and smart mobility solutions. Welcome to our FTP and thank you for accepting our invitations.
Thank you, Justin. So, I am James Joy. I think we are good to start. So,
Yes.
today's topic is AI in automotive. Um, so, I have some 30 slides. We can go through it for the next 1 hour. So I will try to give an introduction and an overview of what is happening in automotive software development and where we are in embracing the AI technologies. So we will start with some all the evolution part, then we will go to the AI area. So let me just a second. Is the slide moving?
As slides are moving, I can see slide number 2.
Slide number 2. Okay. So, uh, so in Tata Elxsi is an engineering service company. Uh, it's mostly the difference between, say, for example, Tata Elxsi is again part of Tata Sons. One of the other service provider in Tata Sons is TCS. So one of the difference between TCS and Tata Elxsi is, so we specifically in the niche engineering services area, and Tata TCS will work with everything under sun. So uh, these are the business areas we are mainly focusing on. So one is transportation business unit where I belongs to. Next is media and communications, covering the OTT, 5G broadcast, TV, set-top box, those areas. And there is a medical division, medical equipments, imaging, covering all those areas. And we have a newly introduced digital and AI business unit, mostly cloud transformation, cybersecurity, and that is actually a horizontal unit giving support to all these business areas. And Tata Elxsi has an industrial design, so mostly mechanical and in design areas. So this is an overview of the company in which I am currently working. So I have from the last 2 decades working in the transportation business unit. We can go to the automotive uh, ecosystem. So we should have some understanding on the ecosystem. So there is OEMs. So we all know OEMs. Tata Motors is an OEM. So the original equipment manufacturer. So they uh, build the car and sells the car. But traditionally, these OEMs are not developing any systems or technologies. Actually, they have an assembly line where cars can be produced. That's a factory, and they do the market research. They do the sales and support to after service, after market areas. That's a traditional OEMs, but and there were tier one suppliers, so they will produce uh, technology solutions and everything, electronics as well as other components, everything, because it's a collaboration of multiple stakeholders, because not a single company can do everything. So there are tier one suppliers, say for example Robert Bosch, Continental, Denso. They are the mostly heard tier one suppliers. There are tier two as well as tier three suppliers actually supplying to the tier one or tier two suppliers. So we at Tata Elxsi is a software supplier. So maybe we are sometimes we are supplying to the tier ones or maybe to the tier two suppliers. There are, but in modern day OEMs are actually they are also into defining or generating software in house. So we are even supporting OEMs for uh, software development. So this is the ecosystem, at least in the say software and electronics ecosystem. So then so I have structured the presentation in such a way that we can go through the evolution of automotive electrical architecture, electrical and electronics architecture, and we can see how the electronics came into automotive and the transition to a complex software, and finally, are we ready to embrace the um, AI into the car? And I have another set of slides which is talking about the software revolution. So how the software started in car and how it is evolved into a complex software solution, and are the software is ready for a including the AI into it. So and finally, we have a session, a set of slides on the what is inside car and the AI. AI is not a future. Actually, AI is already there. But if you ask current present day cars with the AI technology in it, I would say very little. It's very limited inside the car. It's not because it's not possible, but there are standards, functional safety restrictions, or cybersecurity restrictions, because the current AI models and the micro or silicon are running on the models are running on the silicon. So even the silicon or the models not ready for all the functional safety standards and cybersecurity standards, which is mandatory for automotive world. So we are there, and it's not the future, and it's already there. So if you look at the automotive electronics and electrical architecture, so in the early day automotive vehicles, so there were only mechanical parts. Then they started adding new features without limitation of the mechanical world. So then the only solution was electronics. So then they started adding electronics into the car as a individual selected boxes. So these boxes, they keep on adding whenever they planning to introduce a new software or a new feature into the car. They keep on adding new boxes into the car. So when we are adding a new box into the car, there will be a lot of sensors attached to the box, and there will be a lot of actuators attached to the box. So, and when the number of boxes increases, number of sensors and number of actuators also started increasing. This is actually a problem inside the car, because there will be wiring connecting all these sensors to the ECU and the box and box to actuators. So wiring we call harness. So this harness has to be somewhere underneath the vehicle. Somewhere has to be there. It is the vein of the vehicle, but it should not be visible to outside world. So as the wiring increases, actually the complexity started. So it adds to the weight of the vehicle, as well as because all these wires are carry current and voltage, so there are chances of smoking. So the first evolution was they introduced network into the um, into the vehicle. So the network is actually by that time some suppliers came up with a very beautiful networking technologies such as CAN is a distributed that enabled the distributed implementation of features, so that a number of sensors and actuators are reduced, because one sensor which is available in the network is available to every other boxes in the same network. So if you look at the evolution, you can see the first part of the in the diagram, where individual buses connecting multiple boxes. So, and all the buses are terminated into the blue big box, that is the gateway. So you can see that gateway is the connection to the external world, where we can connect maybe an OBD device or a tester in the service center. It can communicate to the individual buses through the individual buses to the individual boxes in the car. So this is again, so connecting multiple buses to a common gateway gives some room for development. But again, as and when the number of boxes increases, they came up with a domain based architecture. That means, so the central gateway connecting with few domain main controllers. So these boxes are having multiple slaves. Say, for example, powertrain is a domain. So all the elements or ECUs in the powertrain are connected to the powertrain domain, and the powertrain domain is communicating to the gateway or other domains, so that so the other, say for example, infotainment domain is not aware of exactly how many boxes are there in the powertrain domain, because it just talk to the powertrain domain. So that is maybe many of our current modern cars are having this domain level architecture. So mainly powertrain, infotainment, chassis, and body are the domains, and all these domains are connected to the gateway, and these domains can communicate with each other with even more data centric Ethernet network. So that solves many of the problems in the previous generation networks. We have a very high speed gigabit Ethernet available, and the slaves are abstracted under the domains. So and the number of slaves can be limited or reduced, because the domains are high performance microcontrollers or SOCs already inbuilt to that, so that number of features can move from the slaves to the domains. And the slaves, it's almost like a hardware box with communicating with the sensors and the actuators. So that's actually increases the complexity of the software inside the domain modules, but reduces the complexity of slave modules and reduce the wiring of the entire vehicle. So at this point, some of the cars already started or moving to a new architecture, which is zonal architecture, where instead of having multiple domains, and because the domains are based on the features, because powertrain domain means all the ECUs in the powertrain are connected to that domain. Instead of feature-based connection in the zonal architecture, they moved to a position-based connector. So the driver side, front driver is a zone, front passenger is another zone, rear driver is another zone, rear passenger is another zone. So mostly four zones with, so these zones can be connected to a high performance computer, which is a central unit, and that also act as a gateway. So actually what happened, traditional automotive OEM, all the OEMs are currently producing their cars mostly on the domain based architecture. But some OEMs, say for example Tesla, when they entered the automotive world, they came up with a all new electric cars, and they never built any ICE internal combustion engine cars. So they into the market with a new technology, with everything, even consumer, beyond the consumer imagination. So they really succeed in that. But their architecture was something similar to the zonal architecture. So and maybe that's the reason why all the OEMs are currently moving to a something similar to the zonal architecture, because it's already proven, it's working, and it's already proven in the Tesla, maybe even BYD. All those new generation manufacturers are using a zonal architecture. So how we know about the zonal architecture Tesla, because people started, after getting the Tesla car, they even OEMs, they started tearing down other OEM cars. So we can see that other car manufacturers, how they are packing, how many ECUs are there, how they are achieving the less weight, and wiring harness, how they can reduce. Everything is analyzed separately. So instead of moving or finding a new all new architecture, so we can embrace the what is available in already in the market proven architecture, that is a zonal architecture. So everyone is towards the zonal architecture. So in the zonal architecture, we have a option for a high performance computer connecting all the zonal ECUs, which is actually maybe an enabling point for running say AI inside the car. So once we have all the infrastructure is ready, functional safety compliant controllers are ready, cyber security standards are met, we can really run an AI based algorithm inside a high performance computer. So that will happen. So that means we are almost near or we are ready to embrace AI when it comes to a zonal architecture or a central architecture. Because in the next step for the zonal architecture will be a central compute architecture. So in the because currently we have a limitation of we need so many switches, we need so many actuators, because every window has a window lifter, every window has there is a mirror in the front side, there are lights in the front, there are brake lights in the rear. So there are a lot of sensors in the powertrain area, because all these are has to be wired. But there are new technologies coming even in to reduce the number of wires. So there is something called E2B, Ethernet to Edge bus. So that is that will provide gigabit in Ethernet connection to the sensors and actuators. So actually, smart sensors and actuators through Ethernet itself, so that the central computer, which is a very high performance SoC, which can run neural deep network algorithms, that can connect to the sensors and actuators through an Ethernet, so that we don't worry about the electronics, because electronics is inside the sensor or actuator itself, which is smart, which has Ethernet connectivity. Is something like a edge computing. So some level of processing will happen at the edge devices, and it can process the data. One level of processing, after one level of processing, the processed data can be sent to the central compute, maybe one or two or three central compute devices, and it can send control signals to the edge devices through Ethernet itself. That is the ideal architecture everyone is focusing it. The technology is not yet ready for a production level, but it's proven E2B versus are possible, and that may be the future with automotive with AI in it. So if you can just, so it's just a comparison, not that we can just see the differences, but not that. So actually this, when it moves to the central computer architecture, so we need the automotive Ethernet has a major role, including E2B, and we have high performance computing devices. So already market NVIDIA is coming up with a Thor NPU, neural processing unit. The name is Thor. So these devices, when it is comply with all the security safety standards, so it can be part of the central computing device. So there is something called OTA, over there updates. So that will enable updating the feature when it comes to the AI or a software defined vehicles. We'll come to that. So there is something called software defined vehicle. So just like software defined radio, software defined network, we heard about those terms. So there is something like software defined vehicle is coming, where and there will be a lot of software or more and more software into the vehicle, and with the minimum standard mechanical mechanical devices. So that software defined vehicle can be updated at any point over there in every component, and the feature updates will happen throughout the life cycle of the vehicle, so that we can introduce a feature at any point of the life cycle of the vehicle in a very easy manner. So you need not go to the service center for a software update. So this feature is already available in the domain architecture area itself, but we can update the software of domain modules, not on the slave modules. There are limitations, but when it comes to the central controller based architecture, so everything is in high performance computer, and there is no limitation on the memory or a network connectivity. We can update the software, download the software into the vehicle, and update when it is ready. So that will open doors to very vast set of use cases. So we will see that software defined vehicle. So altogether, we can see that the architecture evolution already happened, not targeting AI, but targeting a need of the hour plus autonomous driving. So because when it comes to the autonomous driving, there are already autonomous cars, because we have already seen Tesla driving the car from the factory to the owner. When he books a Tesla, after when the delivery is ready, the car automatically drives from the factory to the owner. So it's already happening. So sorry for the other extra noise. Autonomous driving needs certain infrastructure. So maybe that is one of the driving factor towards the central compute architecture. That's what we can understand from the overall evolution of the architecture. But once the centralized computer architecture is ready, so we need not introduce autonomous driving. So actually, on top of the centralized architecture, we can easily introduce the AI. Then AI will be an enabler for autonomous driving, because we will get a lot of computing power, and the algorithm benefits when it moves to the AI first. Then the AI will enable the autonomous driving in the car, because we have seen that, like battery electric vehicles, when it into the market, there is no automatic transmission, because electric cars itself is an enabler for automatic transmission. So just like that, so when the AI is into the central computer architecture cars, autonomous driving will easily followed. So the future outlook will be, the network outlook will be an AI core. So that, so we are targeting something beyond 2030. So everyone, but maybe the Tesla or BYD may come up with a even before that AI-enabled car in the near future, because they have no restrictions. All other OEMs, they have heavily invested on the conventional assembly line and the supply chain and the entire ecosystem. So they cannot easily transform to a new technology. That's one of the difficulty currently all the major German OEMs are facing. They can even compete with the electric cars produced by Tesla or BYD. It's very difficult, because the investment and the technological achievement they have already made is not directly related to the electric cars. So there are a lot of differences. So, but everyone will move to an AI-based transportation area in the near future. So now we have seen the evolution of automotive electrical architecture. So where we come to a central computer, maybe a supercomputer inside the car, which makes our car similar to a smartphone with different feature updates every 6 months or every month. It's possible. So next we can go through evolution of automotive software. So initially, when I started with automotive development, it was a legacy monolithic software development. So that means we have a special hardware. On top of that, we have maybe a microcontroller, and sometimes even not a microcontroller, but a silicon logic inside with a very minimal interfacing for the software. So we have written software on top of specific hardware so that software and hardware are very tightly coupled. So when started adding more and more software modules, each supplier or each OEM or each supplier has their own software architecture. So when the same supplier is providing a software for another OEM in a distributed network, it's not possible, because in the distributed network, everyone shall follow CAN network communication, as well as there are some network management protocols. So they realized that in the automotive world, we need a standardized software, and everyone agreed on that. And all the OEMs, all the tier ones, they started a consortium, AutoSAR. So AutoSAR is a system architecture plus software architecture. So it starts from car as a system. So we can design from there until we will start designing car as a system, and we can add, so individual features are components, and these components we can assign to a particular ECU unit, and inside the ECU unit, AutoSAR will provide a platform. So on top of the platform, we can implement software components. So it's a standardized environment. There are platform providing companies, Vector, Electrobit are some of the providers. So we can buy everything under the orange color part. ECU hardware will be by the supplier, mass production supplier, and what comes between the ECU hardware and runtime environment, including the runtime environment, or between runtime environment and hardware, is a platform which we can buy from commercial off the shelf as a product. Then it can be configured for individual requirements. There is a typical ECU may have 5,000 parameters to configure. So we are not writing code for the platform side, but we can design it and we can configure the platform. It's not easy, but it is possible. There are tools that supporting configuration, and finally the runtime environment is generated based on number of features hosted on top of the runtime environment. So that is how they introduced a standard software platform. So by introducing a standard software platform, they incorporated all the existing, all the know-how of the tier one suppliers, OEMs, everything is incorporated because it's shared. There were many patents, so they broke the patents, and everything is shared public so that everyone can use a standard platform. So that is already available, and this is the hot topic currently in the automotive software development area, but it's almost ending the legacy of the AutoSAR. So when they started the AutoSAR, it's just AutoSAR, and now they renamed it as AutoSAR Classic, because it's a classic system right now, because there are new forms of software architecture in place. So they also introduced all the safety, security standards inbuilt to the platform. So we developed most of the software in the last decade in the AutoSAR based solutions, and most of our cars are currently having AutoSAR based ECUs, because it's like a plug and play. So you can buy one ECU from one supplier, another ECU from another supplier. just make sure that your AutoSAR version matches. Then you can plug into the network, because all the network management protocols, everything will be same because it is standardized. So, but there are limitations in this architecture because it's again it's standardized, but it's tightly coupled because all these components, there is no dynamic behavior possible in this architecture. It's, if you want to change something, you can easily change it. You can configure, reconfigure. You can change the logic in the software component, but you need to compile and create a new software which cannot be flashed easily. You have to deliver the new software to the service stations, and car has to be flashed when it is available in the service station. That we are seeing already. If there is a problem in the software, when we go to the service station, they will reflash the our EC with the new software. So, but when they started developing autonomous vehicles, they realized that it's not enough. We need something dynamic. So they introduced AutoSAR adaptive. So where it's in the classic part, it has a lot of dependency on the hardware, IO devices, motor controls. So when it comes to the adaptive, it's a network-oriented, service-oriented architecture, where instead of components, all the features are implemented as services. So, and these services are implemented based on C++, which is having a dynamic binding capability. So that is being used in the as a dynamic, introducing the dynamic behavior into the software. You can introduce a new feature as a service installed to the car if car supports OTA. So this is already in place in some of the vehicles where you can OEM can update or add a new service into the car through the OTA in the domain, mainly in the domain ECUs. Or Tesla is already having in their central computing device and zonal ECUs. So it is a proven thing and it is already in production. So it's a POSIX based ECU, and the service platform foundation and all the services are running on top of POSIX, and below the operating system can be any POSIX OS, and it can even be a hypervisor which is hosting multiple operating systems, and even on top of multiple operating systems we can have multiple ECUs possible in this adaptive environment. So software is also evolved from a legacy tightly coupled software into a standardized or runtime environment to a adaptive service oriented architecture. So again, it's just a comparison. You can have a quick look what is happening. When it comes to adaptive service-oriented architecture, SUMIP is the one of the communication protocol underlying used in the communication service, or the service discovery and service implementation. Or you can also come with the DDS, and the processors are also very high performance processors are currently available, which can host multiple ECUs on top of a hypervisor. So most of our ADAS systems are currently running in the adaptive service-oriented architecture. So now we are in a new, so this is a new buzzword in the automotive industry, software-defined vehicle. So this, it can be on top of our adaptive AutoSAR, or it can be a all new software architecture. So different OEMs has different strategy. So if somebody wants to introduce something or try out something, so everyone is relying on adaptive AutoSAR, where we have already service-oriented architecture is implementable, and over there updates are supported, and it has dynamic behavior. So some are even analyzing, introducing a all new software, because OEMs are trying to convert their mechanical assembly line into a software factory, so that assembly line and the number of mechanical parts in the car will be very standard, limited. So they are trying to transform the OEM itself into a software factory, and so that they can own everything and they can introduce a new feature at any point, because the vehicle supports OTA. That's very much advantage in terms of cost effectiveness for the OEMs. So the future will be a cloud car. So vehicle can communicate with all the adjacencies, infrastructure, car, vehicle, other vehicles, or network, or even people. So it's a cloud-based car, or there is something called digital twin that we will see in the coming slides. So this is the future. So software has evolved from a very crude architecture to a centralized, dynamic, over there update possible software architecture. So that means we are ready for AI into the car, because, or maybe targeted implementation was autonomous car. So we are ready for a autonomous car with AI inside the central computing device. So both hardware and networking architecture as well as the software architecture are towards an AI powered supercomputer cloud-based car. So that's where we are, the AI revolution. So we are near, or we are already in the AI revolution. It's not the future. So this is what digital twin. So when it comes to a central computer based car with a very dynamic software architecture in it, then the next thing will be integrating with the cloud, so that the entire car will be having a twin digital car in the cloud. So you can see the representation. So the physical car has a digital twin in the cloud. Once the digital twin, each car will be having a digital twin in the cloud space. So once this is ready, it's a major leap into the technology area, because inside the virtual or a digital twin car, we have a lot of tools in the cloud which can sorry, which can interact with the live data in the physical car. So where we can run a AI-based algorithm in the cloud, and we can give the response back to the physical car, where driver can see many features. So it's beyond the imagination actually. So whatever possible in the AI world can possible in the real physical car scenario, without compromising on processing power, or a connectivity, or safety, security. Everything can be ensured in the virtual space. So there are a lot of advantages when it comes to this digital twin. So it's not only the car, each and every signal in the car will be reflected in the digital twin real time. So if the car is driving at a particular speed, engine is running at, or motor is running at a particular RPM, the same RPM will be reflected in the virtual space as well. So this will provide lot of, it's not only inside the car, so it can have a physical digital twin. So 3D models can be there in the cloud. So it can the factory building these physical car, it's using a lot of robotic arms. So these robotic arms are also having a digital twin in the because the entire factory with the collaborated or all the inventory, all the other collaborators, everyone has a digital twin in the cloud. It's like a automotive metaverse. So everything is possible in that metaverse. So even individual car status, everything is available to the driver. And even in the service, we have something called predictive maintenance, because all the data are available in the car. So you can see that when it comes to the it's a data driven so that means your battery status is depleting, or the health of the battery is going down. So maybe in the near future your battery has to be replaced. So everything can be analyzed from the cloud, and the information can pass to the physical car or to the driver. So need not worry about the maintenance when it comes to the digital twin world. So the car can automatically go to the service station and do the maintenance, or it can receive update from the OEM, or it can communicate with the OEM. If everything is possible when it comes to this data centric approach. At the same time, the manufacturing, there is the assembly line will never be shut down, because all these robotic arms are having a digital twin, and if anything goes wrong, or any maintenance is nearby for any of the robotic or the assembly line, it will be communicated in advance. So shutting down the assembly line is a nightmare for the manufacturer. So it should not happen. So in this world, they can optimize their production, and there won't be any shutdown in the plant. And all the supply chain optimization is possible, because whatever inventory, the current status of inventory and the status of inventory at the tier one supplier side, everything is tracked, and that is automatically available in the factory when it is in need. It's a just-in-time technology. So it's again, there will be also similar to the digital world, there will be a 3D models available, so that they can test their new aerodynamics models. No need of so expensive testing facilities. So it's everything is possible in the cloud area. So just trying to go through all the possible scenarios. We are not going to deep into any of these areas. So another possibility when it comes to this digital twin, so the digital car can drive millions of miles without even actually without the physical car. So they can fed the road scenarios into the digital car in the cloud, so that they can train the AI model in the digital car by learning all the scenarios, whatever available. So there is no limitation for training the car. So once everything is proven and they verify the working of the digital car, and the digital twin can download the software into the physical car. So the self-driving implementation or training or all the scenarios can be covered very easily in this digital twin scenario. So that means so every OEM will be targeting a AI into the car first, then they can achieve autonomous driving very fast and most reliable way. So even if you look at Tesla is making mistakes at some special cases, because it's how much we can train a physical car, that is a limitation. But when it comes to the digital twin or a digital car, there is no limitation on the training, but it's only data collection. So the return on investment we have already seen, there will be a huge cost reduction, and they can come up with new features into the car. Time to market will be very much reduced, because nowadays traditionally, all new car into the market means it's 4 years. So we start because we started working with a all new model in 2012. Then the car is released in the market in 2017. So 4 or 5 year period is the standard um, uh, introduction of a new model into the market. So, and it involves huge cost for the OEM. So generally OEM won't do a all new model into the market. They will always rely on carryover. So there is no car or it's very rare something all new come to the market. It will be carryover from existing model with a few modification, because all new model is a highly expensive and time consuming process. So everything will be reduced when it comes to the this kind of digital car. So these are the technology enablers to achieving a digital car. So we all these technology areas are already proven in the consumer world. So when it comes to a automotive or a transportation area, so we need to perform certain analysis on the safety, security. So that is maturing the technology, but the technology is already proven and it's already there in the consumer world. So there is something called connected cockpit. That is another AI into the vehicle, because we don't call the instrument cluster as a cluster route in the future cars. It will be a cockpit. So it is an integrated display of multiple units with all information in front of the driver, and even the driver will be monitored by the cockpit itself, detecting any drowsiness or a fatigue in the driver face, so that maybe the car can take over the control, or car can safely drive away from the motorway into a adjacent lane for a hard shoulder for a safety parking. So connected cockpit is another AI related topic inside the car. So most of the interface for the driver will be inside the cockpit, just similar to a aeroplane cockpit. So everything is available in the central cockpit unit. So autonomous vehicles are, because once we have the central cockpit architecture plus digital twin, because then the autonomy will automatically follow that. Perception, it can happen in cloud or inside the car with the central NPU module, neural processing microcontroller. So the decision making and even the control, everything will happen in a split second by the high performance computing devices in the car. So we know already it's a projected market for the AI inside the automotive segment. It's next 5 year, maybe. So maybe 2030, there will be cars with AI in it, most of the autonomous features in it. So it will be threefold or every 5 year. So we can see that it's there are vulnerabilities or risks when it comes to a high computing power with a high level of network connectivity for a moving vehicle with people in it, and on road where also people are available in the road. So there are already standards for the safety. ISO 26262 is a safety standard where multiple levels of safety integrity levels are specified. So even there are vulnerabilities, but once everything is standardized, so we can reduce these vulnerabilities to some extent. But still, anyone can hack any of our software if enough time is provided. So it's and whenever a vulnerability is detected, so one of the advantage here now is definitely there will be vulnerabilities. So, but if any vulnerability is detected, we can update the software, fixing it and update the software very easily through the over-the-air updates. So, towards 2030, we can see that new neural processing units are coming, chips with deep neural network capabilities integrated or into the silicon itself, so that we can achieve real time. Because there is nothing acceptable in automotive world without real time processing. Because that's one of the reason we even and the traditional cars are not having any Linux in it or any soft real-time systems. Not possible, because we only rely on hard real-time systems, and the cars will even discard the even some data which is 10 millisecond older. They will just discard the data, because not even a delay of 10 milliseconds is not acceptable in most of the cases when it comes to the safety critical environment. But there are NPUs are coming with neural networks are already implemented inside the silicon, so that they can ensure real-time behavior through that chips. So communication, again another backbone network needed between cloud and the car. So, but we can buffer a lot of data in the car even without any interruption in the communication, because the network or silicon is memory area or RAM, ROM, everything is abundantly available in modern day cars. So when it comes to human and autonomous driver, AI driver, we know that AI driver is always having precision and accuracy. So when we can embrace this AI technology into the car with keeping all the safety and security vulnerabilities addressed, then definitely it can be a more precise and accurate driving experience. So I have finished overall that AI topic into the automotive world. Hope you receive some insight into what is happening in the automotive world and where we are with respect to AI and development wise. So if you ask what development we are doing inside automotive world for the AI at the present, it's very limited or very little. But in the future, there will be a lot of AI coming into the car. If you have any questions related to this, we can discuss.
Participants, if you have any questions, you can ask.
Justin, if there is no questions, we can wind up because it's already late for everyone.
If no more questions, we can wind up. Thank you, James, for a nice session giving an introduction to AI in automotive. Thanks again.
Thank you all. Bye-bye. Good night.
Thank you all. It's end of today's session. Thank you.